Hello, physics students. Hey, we started looking at friction in class. What I'd like to do today in this video is solve some of the problems that were at the back end of that presentation. So what I'll do here is give you a quick review of the topics from class. You might remember that we learned about static friction and understood that that force is always going to be less than or equal to some maximum amount of static friction, which is calculated by saying coefficient of friction, coefficient of static friction, that is, times the normal force. And we made a distinction to say this is the maximum possible friction we could have, static friction. And we noted that we don't always get that much. We only get what we asked for, so that the thing doesn't move. It counteracts what we are demanding of it, and no more and no less. That's why the less than or equal to sign is not an equal sign. It's because these two numbers are usually different. Back here, mu sub s times F sub n. To look at that in terms of a force diagram, you'll see in the force diagram that the force of friction has to balance the applied force. Otherwise, the thing would be moving. So all we get for force of friction is what we ask for. And we kind of, with a wink, say that's pretty amazing. Like somehow the friction knows how much to pull, just enough to combat the static friction. We also looked at it graphically, and we said that the applied force and the friction force are related very simply. You get what you put in. If you apply a little bit, you get a little bit. If you apply a medium amount, you get a medium amount. And so on, all the way up to some maximum. And that maximum is really interesting because we can calculate it. And we learned is that the maximum amount. Here are some real coefficients of friction. We're going to use these two in the example, so it's probably worth jotting them down or just memorize them. Ice on ice is 0.1, and wood on wood is 0.4. Let's try this first example. I'd like to suggest you pause the video and try it first before you hear the explanation. Okay, we're back from the paused video, and we'll talk about how this is done. Now, the question is, what is the force of friction? Well, if this thing is not slipping, then the force of friction would be 10, right? Because it's not slipping, and that would be what we would need to counteract the applied force of 10. But we better check and make sure it's slipping. That is, we better check and make sure it's not slipping. So let's do that. Is the ice block slipping? I don't know. But we can say that the maximum, the force of friction max, that's static friction. Boy, we have a lot of subscripts there. Force of static friction maximum is going to be equal to mu sub s times F sub n. Mu sub s, we remember just from the last slide, is 0.1, and because it's ice on ice. And then F sub n is, we can just eyeball that. We see that the weight of the ice is 110 newtons, so F sub n is 110 newtons. If that's not obvious to you, remember that the vertical forces on this thing are F sub n and the weight, also known as F sub g. And because those must be equal, because I know the thing's not accelerating up or down, that's how I know that F sub n is the same as the weight, which was given as 110. Finally, I do the math, and I get the number 11 newtons as the maximum possible force of static friction. Now, it's tempting to think that unknown force in the diagram is 11, and it's actually a common, I guess, mistake that people might make is say, oh, I calculated it to be 11. But just remember that when we do this calculation, we're calculating the maximum possible We're not trying to calculate the force in the current situation. And so the correct way to think about it is the force in the current situation. We're asking for 10, so we get 10. And that's the correct answer, 10 newtons, to the right to be precise. Good, let's move on to the next problem. What I'm going to do this time is wisely, I will first try to answer the question about whether it's slipping or not, and then after that, determine the force of static friction. And that's actually the correct order to be doing the thinking in these kinds of problems, because if you discover that you're pulling too hard on the object, then you're no longer in a static friction case. And I'll tell you, in this presentation, we are looking at the static friction case in all situations, but soon we'll be studying sliding friction as well. And you're going to need to do that test before you do any further problem solving once you're good at doing both sliding and static friction. So let's do that check. Is the ice block slipping? I don't know. Let's find out. It's the same idea as last time. I have to calculate the maximum force of static friction. Maximum is going to be equal to coefficient of static friction times the normal force. What is the normal force? Here's the twist in this problem. We don't give you the weight of the ice, right? So what you're seeing there is the mass of the ice, and it's easy to get mixed up. You might say, oh, that's the weight, and oh, the normal force is 20. But no, pay attention, because this is kilograms, and if you're given kilograms, that is a mass. And so to convert that to weight, we have to say that the weight is equal to the mass times 9.8. Remember that equation, right, from the last time? I'll do that one in my head. I get 196 newtons. Now I finally have a weight, which is great, because for the same logic as before, if the weight is 196, then the normal force is 196 newtons. Phew, finally, I've got the normal force. I can do the easy calculation down here, 0.1 times the normal force of 196, and that is equal to 19.6 newtons. Now I got to do my check. Is it slipping or not? The maximum possible is 19.6 newtons. I'm only asking for 5, so I'm in the good zone. I'm cool. This is definitely static friction. We're in familiar territory. All of that was to answer question number 1. That's the hard question. The easy question, now that we've convinced ourselves that it's not slipping, the easy question is this one. What is F sub F? F sub F? It's whatever we asked for. And here we asked for 5 newtons, so we're going to get 5 newtons in that direction, pointing to the right, just enough to counteract our pull. Let's go on to the next problem. I'm going to pause the video here again, or ask you to pause the video and try this problem on your own before I reveal the answer. Okay, if you paused your video, we are back now, and we're going to do this calculation. It's pretty much the same as the ice problem. The only thing that changed is that we are now using wood. So you probably, if you were thinking about it, updated your coefficient of static friction to be 0.4. And now we're given a weight directly. We don't have to do any conversion. So we know the normal force is equal to 100 newtons by the same logic we've been using all along. We have mu given, right? So the maximum we could get from static friction is 0.4 times 100, and that gives us 40. So we're able to get 40. We're only asking for 20, so we are definitely not slipping. Now the easy question, if we're not slipping, we must be in static friction. All we have to do is say we get what we asked for, and that is force of friction is equal to 20 newtons in that direction. So in this case, it's pointing to the left because it's opposing the applied force, which was given as 20 to the right. Let's go on to the next. We said that the maximum was 40 in this situation. But first, we need to introduce a new concept. It's called the frictionless pulley. So if you can imagine that circle in that picture as being a wheel that rotates freely around its center, it can rotate either way. So I can make it spin this way, or I can make it spin that way. And if I pull on one string, it's just going to wrap around. That force is just going to wrap around and pull on the other side of the wheel. So without proving it here, I'd like to propose that we accept the fact now that the force of tension on string 1 is the same as the force of tension on string 2. Or actually, I'm sorry, it's all the same string. So we're just saying that the force of tension here is the same as the force of tension here. And we can use that knowledge to solve problems. The pulley is a kind of a handy tool for changing the direction of a force without losing its forcefulness. So that's how we're going to use it in the next problem. Ourselves here. Pretty typical situation here. We've got a wood block on a wood table, and we're going to hang a 2 kilogram mass from the hanging string. What I'd like you to do now is pause the video and try this problem, see if you can find out whether the wood block is slipping and what is the force of friction. Okay, we're back now solving this problem, and we're going to first notice that I was given a mass here. So I'm going to just convert that to kilograms right off the bat. Multiply times 9.8. I'll do that one in my head. It looks like I've got 19.6 newtons is the weight. And if I consider that weight and the string it's hanging from, F sub G or W, either way, that's just the same notation, equals 19.6 newtons. That's the downward force. And then the force pulling up is the tension in the string. So that's a simple force diagram of the hanging weight of the vertical part of the system. But as mentioned earlier, that tension passes right around the pulley, and I can say that therefore the force of tension on the other side of the pulley is also the same as the force of tension to start, which I knew to be 19.6 newtons. So now I've got the force of tension. It's going this way, of course. It's pulling that way because that should be evident, I think, self-evident from the picture. So the question now becomes, what is, excuse me, I just got to check my buttons here. Okay, good. The question is, are we slipping or not? And static friction times the normal force. We did that calculation earlier. We said that that was, and if you forget how we did that, you can pause here and recalculate that. I'm just using our earlier work to know that that's the max. That's the force of friction max. Okay, so if the maximum I can get is 40 and I'm pulling on it with 19.6, I can say the wood block is not slipping. Again, all of that is the hard part. The easy part is what's the force of friction? And because I know it's not slipping, it must oppose the applied force, which in this case is the force of tension. And so force of friction is 19.6 newtons to the left, which I'll indicate as with a negative sign. So there's our answer for that one. And we're good to go. Let's do one more. I call this the challenge problem. I would suggest that you pause the video again and try to solve this on your own. I'll give you one hint. It's helpful to think in terms of components, and that may help you. Okay, so pause the video here, and I'll be back with you in a moment. Okay, we're back trying to solve the challenge problem. We are given a force pulling at an angle on a block of ice. So I'm going to just already note that mu s is 0.1. That we learned from the earlier table. We just looked that up. By the way, that number just comes from some experiments. There's nothing magic about it. A bunch of people tried a bunch of blocks of ice and came up with it's pretty close to that number. So that's what we would say an empirical value, just something that's observed and measured in real life. Now, we started with the hint that maybe we want to think of components. So what I'm going to do is, right off the bat, break my 14 newtons into components. So there's a vertical component, and there's a horizontal component. I'm going to convert the magnitude and direction, which was given as 14 newtons, and I'm going to rewrite that as its components. You could take my word for it that it's 10 newtons in both directions, or if you want to see the math, you can check on your own, because cosine of 45 is the same as sine of 45 is 0.707 roughly. So I'm rounding off to about 10 newtons for the two components. You can check that offline. Now I have my components. Is the block slipping? Here is an easy place to overlook an important element of this picture. Right now, the vertical forces shown are 10 newtons, and let me add the others. There's F sub g, and there is a normal force. I'll just squeeze that in here. I don't have the right lengths here, so just because it's getting a little crowded. But the point that we want to think about here is that the normal force, F sub n, is not simply F sub g in this case, because I put in some extra 10 newtons of help for the normal force. So it doesn't have to work so hard anymore to hold up that block. I'm helping it with this 10 newtons. So F sub n is F sub g minus 10. And that means it's 100 newtons. So convince yourself that that's correct. It's much like the example of me pushing down on a book earlier in the presentation from class, where if you change the applied force on something, that will affect the normal force. Now that we know the normal force and we know the static friction coefficient, we can say the maximum possible friction we can get out of this is 10 newtons. Maximum possible we can get is 10. Now I'm going to check and make sure I'm not asking for too much. Whoa, I'm asking for 10. I am right at the verge. Well, let's see. The equation says less than or equal to. I guess I'm equal to. On a technicality, I'm going to take this and I'm going to say, no, it's not slipping. But boy, if I pulled the tiniest little bit more, yes, it would be. So I'm right on the edge there. If I was an engineer, I wouldn't accept that. I would put some margin in. But for here, we're just looking at the exactness of it, and we're going to say yes, or no, it's not slipping. So given that, what's the force of friction? Here's the easy question. Force of friction is equal to 10, because that's what we asked for. 10 newtons to the right. So I don't need to put a plus or minus on it. All right, that's all we've got. Hope this helped. If you have any questions, as always, you can drop an email.